Now we have to discuss the class A power amplifier with transformer load. Previously we have discussed the class A power amplifier with resistive load. The main advantage of the resistive load is circuit is simple, high fidelity, because input signal will be exactly reproduced at the output. The active device conduct for the entire cycle of the input signal. There will be no crossover distortion. Only one active device, transistor, is required. Disadvantage of class A power amplifier with resistive load is power loss across the collector resistor. The main disadvantage is pure efficiency, that is 20%. For improving efficiency, using transformer instead of collector resistor. Class A power amplifier are costly and bulky due to large power supply and heat sink. Harmonic distortion present in the amplifier. There is a harmonic distortions in the amplifier. So efficiency is less than 25%. That is a major disadvantage. To avoid this, we go for class A power amplifier with transformer load. Due to load resistance RL is directly coupled to output circuit of amplifier, the overall efficiency of direct coupled class A amplifier does not exceed 25. Because the current IC passes through resistor RL, there is waste of power. It does not contribute to useful AC power. This problem is solved by using transformer as a coupling device between output of transistor and load. So this problem is solved using transformer as a coupling device. The coupling between output and load and output of transformer, output of transistor. In between we have to connect transformer. The output power delivered to the load will maximum. The output power delivered to load will maximum if load impedance is equal to the amplifier output impedance. Load impedance is equal to the amplifier output impedance. In audio power amplifier, the load may be loudspeaker. We connect load may be loudspeaker which has impedance in the range of 3 ohm to 15 ohm. Impedance is in the range of 3 ohm to 15 ohm. The output impedance of amplifier is of order of 100 to few kilo ohm. Therefore, in order to get maximum power output, the load is coupled to the transistor collector circuit by means of a transformer. The high impedance primary up step down transformer is connected in high impedance collector circuit, and a low impedance secondary is connected across the load, generally loudspeaker. Circuit detail. This is a circuit of transformer coupled amplifier. This is a circuit transformer coupled amplifier. The circuit is a single-ended class A power amplifier. Single-ended class A power amplifier with transformer load at collector. as shown figure. The power amplifier are used to drive the load like loudspeaker antenna, loudspeaker and antenna, loudspeaker and antenna. The maximum power will be transferred to the load. Maximum power will be transferred to the load to the load from the power amplifier only if its output impedance is same as the input impedance of loudspeaker. The transformer provide impedance matching. That is a great advantage of transformer. The circuit consists of NPN transistor in CE mode. Transistor is connected in CE mode because we take output across collector through the transformer secondary. Secondary is a step down, so its input impedance is very less, which matches the loudspeaker. R1 R2 are used for potential dividing biasing. RE used for thermal stabilization. C is a bypass capacitor which prevents the negative feedback by the effect of RE. The primary of transformer is connected to collector of transistor and VCC. The load resistance RL is connected to secondary of the transformer. In order to have maximum AC power, the peak value of collector current due to input to AC signal alone should be equal to zero signal collector current. In order to have maximum AC power output, the peak value of collector current due to the input AC signal alone should be equal to the zero signal collector current. To achieve this, operating point is located at the center of the AC load line. To achieve this, operating point located at the center of AC load line. The function of step-down transformer is to match the low impedance load to the collector. The value of R1 R2 are adjusted to give the class A operation. The input to capacitor C couples the signal to the base of transistor. It blocks any DC component present in the signal and pass only AC signal for the amplification. So C is pass only AC signal and it blocks the DC signal. Because of this, biasing condition are maintained constant. An emitter bypass capacitor C is connected in parallel with the emitter resistance RE to provide a low reactance path to the amplified AC signal. RE provides bias stabilization. A transformer coupled class A power amplifier, also called single-ended class A power amplifier, because single transistor is used for amplification. The value of resistor, the value of R1, R2 are adjusted to give class A operation. The input capacitor Cin couple the signal to base of transistor. It blocks any DC component present in signal and pass only AC signal from amplification. Because of this, biasing condition are maintained constant. So we have to discuss the operation in order to get maximum AC. In order to get maximum AC power, maximum AC output, the peak value of collector current due to input signal alone should be equal to zero signal collector current. Peak value of collector current due to signal alone should be equal to the zero signal collector current. To achieve this, operating point located in center of AC load line. The transistor remain in the active region throughout this operation. This is achieved by adjusting biasing circuit R1, R2 and RA. When the input signal is applied to base of transistor through the coupling capacitor, the forward bias of base emitter junction will vary between maximum to minimum. Forward bias of base emitter junction will vary between maximum to minimum. The base voltage varies as per the signal voltage Vi. Base voltage varies as per the signal voltage Vi or Vs. As a result, base current will also vary. Base current will also vary. The base current varies accordingly. Collector current will vary. This variation of collector current produce variation in the voltage across the primary winding of transformer. The variation of collector current produce variation in voltage across the primary winding of the transformer. The result is amplified AC. The result is amplified AC voltage appear across primary winding of transformer. It is transferred to secondary winding by mutual inductance, which in turn develop AC power and supplies to the load. In this we have to discuss the impedance matching using transformer. How the impedance is matched using transformer, we have to discuss. Consider a transformer as shown, which is connected to load of the load resistor RL. While analyzing the transformer, it is assumed that transformer is ideal. There is no losses in transformer. While analyzing transformer, it is assumed transformer is ideal and there is no loss in the transformer. Similarly, the winding resistance are assumed to be 0. So we know that transformer is made by using windings, primary winding and secondary winding. Its resistance assumed to be 0. This is a transformer circuit. So V1 is V2, RL is load resistance, RL dash is the what is the RL dash? RL dash is the resistance in the primary winding. RL dash is the resistance in the primary winding. A load resistance RL would be calculated from, we have to calculate load resistance RL equal to, what is RL? V2 by I2 gives the load resistance, and V1 by I1 gives the input resistance RL. Input resistance RL dash. Input resistance RL. Let the reflected load in primary of a transformer calculated from. So RL is reflected from the load, assume it. So it can be calculated V1 by I1 from basic transformer. From the basic of transformer theory V1 V2 equal to N1 into I1 I2 equal to N2 by N1. From equation 3 and 4 we can write, from equation 3 and 4 we can write V1 equal to N1 N2 into V2, I1 equal to N2 by N1 into I2. Substitute equation 5 and 6 in equation 2. We have to substitute V1 and I1 in equation 2. We get in equation 2 is R dash, reflected resistance. So V1 is N1 by N2 by V2, I1 is N2 by N1 into I2. So N1 by N2 whole square into V2 by I2. So RL dash equal to N1 by N2 whole square into RL, where RL is a load resistance, N is a, let N1 by N is a small n, RL dash is equal to N square into RL. So proper selection of turns ratio results maximum power transfer. If you want to match 20 ohm load to the power amplifier, so that effective load may be 8 k ohm, then the turns ratio should be 8000 by 20. 8000 by 20 gives the turns ratio. So if since you have class A power amplifier, we have to calculate efficiency of class A power amplifier with transformer load. We have to calculate. So in a class A power amplifier with transformer load, efficiency is 50%. Next efficiency, we know that the voltage across a transformer, there is a less resistance. So transformer, there is ideally the resistance equal to 0. So apply the KVL to that, we get the drop across primary winding is 0, VCC minus VC equal to 0. So VC equal to VCC. We know that slope of DC load line is given tan theta minus 1 by RL dash. So RL dash equal to 0 ohms. Slope of the DC load line is ideally infinity. Tan theta is infinity, theta value is 90 degrees. Thus DC load line is almost vertical straight line passing through voltage point on x axis, which is VCQ equal to VCC. So this is the load line diagram, AC load line and DC load line. The AC here, DC load line is, its RL value is 0, assume as it is. So DC load line is straight line passing through the Q point. So VCQ value is equal to ICQ. VCQ equal to VCC. So slope for AC load line is minus, DC load line is minus 1 by R. This is the maximum current, ICQ, Imax and Imin. This is a current swing. V minimum and V maximum is the voltage swing. This is a graph for AC load line. From this graph we have to calculate the efficiency. For AC operation, when AC signal source is connected to the input of the amplifier, the resistance in the collector circuit is formed by reflected resistance of load RL dash. The load line corresponding to this resistance is called AC load line and has slope minus 1 by RL dash. This load line is drawn through the operating point Q. This is the DC load line, AC load line. So we know that efficiency is equal to 50 into Vm Im by VCC into IC. VCC into IC is the DC power. So we have to calculate Vm and Im from the shown above graph. V maximum value is 2 VCC. V minimum equal to, assume this, from this we can write V minimum is 0, V maximum is 2 VCC. I minimum is 0, I maximum is 2 times ICQ. 2 times ICQ as shown in the graph. We know the efficiency formula, eta equal to 2 times V max minus V min into I max minus I min by 8 VCC ICQ. So substitute this 2 VCC, 2 ICQ, 2 into 2, 4 VCC ICQ by 8 VCC into ICQ into 100 equal to 50%. So efficiency of class C power amplifier with transformer load is 50%. When AC signal is applied in the base current varies sinusoidally, assuming that non-linear distortion is absent. The nature of collector current and collector to emitter voltage also varies sinusoidally, as shown in figure. As collector current is the current in the primary winding of transformer, varying collector current produce induced voltage in the secondary of transformer. Secondary voltage. The advantage of this is efficiency of increase from 25 to 50%. Advantage of transformer load is the amplifier increase 50%. Load is connected through transformer, therefore collector power dissipation is less. So So power dissipation is a major advantage of this, less power dissipation, because internal impedance is 0, so there is no loss. So VCC equal to VCE. Transformer connected in the collector circuit provide impedance matching, thus any load may be connected across it. Transformer connected in collector circuit provide the impedance matching, thus any load may be connected across it. Disadvantage is due to transformers. Main disadvantage due to transformer circuit become bulky and costlier, and circuit is complicated to design and implement. Circuit is complicated to design and implement. Now next topic we have to go, operation of class B power amplifier. Operation of class B power amplifier. So class B power amplifier, we have to discuss how the circuit will work. So class A operation working angle is, class A operation working angle is 360 degrees. So base current varies from 0 to 360 degrees and collector current also varies from 0 to 360 degrees. 0 to 360 degrees. So here we have to see the need for class B push-pull configuration. Need of push-pull configuration. So here push-pull configuration we are using. Q1 and Q2 are connected as such as push-pull configuration. So what is the push-pull? We have to discuss. We have to discuss the working. The output stage essentially consists of a power amplifier. Its purpose is to transfer the maximum power to the output device. Efficiency of class A amplifier is very low, that is 50%. So efficiency is 50% very low. In order to obtain high output power at high efficiency, push-pull arrangement is used in the output stage. Push-pull arrangement is used in the output stage. The push-pull power amplifier is a power amplifier is frequently used in output stage of electronic circuit. In this arrangement we employ two transistors in class B operation. In this arrangement we employ two transistors in class B operation. Transistor T1 and T2 are placed back to back. That is, Q1 and Q2 are placed back to back and operated in class B operation. That is, collector current IC is 0 when there is no signal. When one transistor amplifies positive half cycle, while the other transistor amplifies the negative half cycle of the signal. In this way, the output voltage is complete sine wave. At the same time, the circuit delivers a high output power to the load. High output power to the load due to class B operation. Because efficiency of class B operation around 78%. Center tapped secondary of the driver transformer is used to supply equal and opposite voltage to the base of the two transistor. So advantage of push-pull amplifier is even harmonic are absent in the output. Problem of core saturation, non-linear distortion will not appear. Problem of core saturation, non-linear distortion will not appear because of cancellation of DC component of collector current. So will not appear because cancellation of DC component of collector current. The output is double as that of offered by the single-ended stage. The effect of refill voltage of power supply due to inadequate filtering are balanced. The effect of refill voltage of power supply due to inadequate filtering are balanced out because of flow of refill current in opposite direction in the primary of output transformer, because the current is in opposite direction in primary of output transformer. So disadvantage of the push-pull amplifier is two center tap requires two transistors, and when there is no input signal, power dissipation is zero. When there is no input signal, power dissipation is zero. Need of use of driver stage at the input to provide two equivalent output voltage. Circuit gives crossover distortion. Frequency response is poor. Need for bulky expensive transformer. The parameter of two transistors are not the same. Parameter of two transistors not same. There will be an equal amplification of two half of the signal. The circuit consists of push-pull amplifier is a power amplifier is frequently employed in the output stage of the electronic. It uses high output power with high efficiency required. The transformer T1 is an input transformer. It's called phase split. It required to produce two signal voltage which is 180 degree out of phase with each other. Two signal voltage with opposite polarity drive the input of the transistor Q1 and Q2. So V1 is positive half cycle, V2 is in negative half cycle. It amplifies. So working when no signal is applied, when no signal is both transistors is cut off, no current is drawn from the supply. No current is drawn from the supply. There is no power wastage on standby. The power dissipation in both the transistors is practically zero. So when input signal is applied, case 2, when input signal is applied during the positive half cycle of input signal, during positive half cycle of input signal, Q1 is a active stage. The base of transistor Q1 is in positive and that of the Q2 is a negative. Results: Q1 conduct while transistor Q2 is on off. When input signal goes negative, Q1 off, Q2 conduct. Thus at any instant only one transistor circuit is conducting. In other words, each transistor handles one half of the input signal. the output transformer joins two halves and produce full sine wave in the load, even though its working angle is less than its working angle is 180 degrees, even though it produces full cycle at the output. So there is no loss of the signal. So this is a Q1 Q2 connected back to back with the input side is transformer, output is the output transformer which match the impedance, and VCC is the proper biasing to the Q1 and Q2. We are applying through the VCC plus VCC. V1 V2 are the input voltage. V1 V2 are input voltage, that is 180 degrees out of phase. Q1 is on during positive half cycle, and during negative half cycle Q2 is on. So due to Q1 on, there is a Q1 on, there is a IC1 current flows. Due to Q2 on, that is below transistor, IC2 is flows in opposite direction. So total current is IC1 plus IC2. So input transformer has center tap winding. It provides equal and opposite voltage to base of the circuit of transistor. The primary of output transformer is also center tapped. Collector terminal of two transistors are connected to the supply VCC through the primary of output transformer. The load resistor is usually loudspeaker connected to across secondary of output. During positive half cycle, that Q1 is positive and Q2 is negative. So Q1 forward bias, Q2 reverse bias. Circuit will conduct due to Q1 only. There is a by current IC1 is flows. This half cycle of signal is amplified by Q1 appear in the upper half of the primary of the output transformer primary. During negative half cycle, Q1 off, Q2 on, and IC2 current flows. This half cycle of the signal is amplified by Q2 appear at the lower half of the output of the transformer. The center tapped primary output transformer combined two collector current to the from sine wave output in the secondary, that is applied to the load. Two transistors conduct in alternate half cycle of the input signal, hence collector current flow in opposite directions, so that net DC in the primary is 0. A collector current flow in opposite direction, so that net DC is 0, and secondary the output transformer will have the induced voltage. Output of amplifier will be twice the output offered by the single transistor. Thus push-pull arrangement permit maximum transfer of power to the load through the impedance matching. So RL dash is 2 times N1 by N2 whole square RL. Advantage is power output is high, efficiency is 78.5, push-pull mechanism avoid the harmonic distortion, negligible power loss at load. Disadvantage measured in crossover, coupling transformer increase the cost and size, parameter of two transistor are not same. Parameter of two transistor are not same. Transformer coupling can be employed only for small load. So transformer coupling can be employed only for small load. If the parameter of two transistors are not the same, there will be unequal amplification of two half of the signal. Now DC power input we have to discuss. Each transistor output is in the form of half wave rectifier waveform. Hence we know the half wave rectifier, which allows only half of the signal. So hence Im is the peak value of output current of each transistor. DCR average value is for half wave is Im by 5 due to half wave rectifier. Two current drawn by two transistor from the DC supply are is in same direction. Hence total DC or average current drawn from the supply is sum of individual average current drawn by each transistor. Im by 5, 2 Im by 5. Here the transistor works less than 180 degrees cycle. Total DC power input is given by VCC into IDC. PDC is 2 times Im by 5 into VCC. The AC load line in slope is minus 1 by RL. DC load line is impedance is 0, so it is a straight line. Q point is occurs at generally VCC comma 0. So only half cycle is allowed. So operating point is in cutoff region. The operating point is in cutoff region. So only Vm is equal to half cycle. So maximum VCC. Im equal to I max. For AC output, Vm and Im are the peak value of the output voltage and output current respectively. Vrms equal to Vm by under root 2 Irms Im by under root 2. Vrms into Irms Vm Im by 2. PAC is Vm Im by 2. So efficiency is PAC by PDC into 100. PAC is Vm Im by 2. PDC is 2 by 5 VCC Im get cancelled. So 5 by 4 into Vm by VCC into 100. Vm equal to VCC. Then from the peak value of collector voltage Vm is increase, efficiency increase. General Vm, assume Vm equal to VCC. So 78.5% is efficiency for class B push-pull amplifier. So Vm equal to Im. Maximum output voltage swing is Vm equal to Im. So with this we have discussed the class B push-pull amplifier. Class B push-pull amplifier, which is two transistors connected back to back. So main advantage is output power is high, power efficiency, push-pull mechanism avoid harmonic distortion, and power loss at load, negligible power loss at load. That is a major advantage. So it provides impedance matching also. But disadvantage is crossover distortion, it increase cost. The parameter of two transistors are not same. There will be unequal amplification of two half of the signal. Transformer coupling can be employed only for small load. Next is a complementary symmetry push pull amplifier we have to discuss. Complementary symmetry push pull type of distortions, amplitude distortion, crossover, harmonic, frequency phase, all these are we discussed. The peak value of output waveform of the power amplifier clipped up due to shift in the Q point. The output waveform is not same exactly input. This type of distortion is called amplitude distortion. This we have to discuss in next chapter.